Okay, so good afternoon, students, for this AMC courses. So today will be the third lecture for this third or fourth lecture, I think, yes, fourth lecture of this our functional materials part two. In the last three lectures, what we have studied with semiconductors, so sweet. So we started with the important semiconductors and their importance is there, and how we are making the. Then we started with how we are making the single crystals. Last class we were talking about, last two classes were all basically on single crystal growth, and then in the last lecture we started halfway we were into the thin films. So we will be continuing with the thin film part today also. And before going into the course content and all, I will say I have received all of your answers. Today also there will be maybe one or maybe two also. I will be putting some questions, and thank you for answering them. Try to answer them by tonight. Maybe 7 p.m. would be good, but at least 9 p.m. But not like tomorrow and day after, because sometimes I am getting answers. Even today morning I got answer. So then it defeats the purpose. So try to be there in the lecture, and because the questions are very small things, which I will be discussing in during the slides. In the slides, it is there. So try to answer them. And if you have got any questions, please feel free to stop me during the presentation, and we can go and revise it. Or if required, you can get back to me again anytime. My email ID is there, and then we can discuss in depth. So now coming to the thin films. So just to revise what we have already started, like why thin films are important. So most materials are generally using bulk, but bulk have got fixed properties like electrical resistivity, optical properties, band gap. So it is fixed for a bulk material, and so their applications are limited, whatever they are used. But when we are in decreasing the thickness of any given material to a given point, like in tens of nanometer or so, so their property starts changing because of the surface effects. So this adds flexibility in designing devices for a particular application. And in many, even like magnetic application, superconductivity, uh, catalysis, or gas sensing. So there are many applications are there in which like thin films are important. And this possess attractive properties are there, which leads to versatile application. And it is easy to grow thin films rather than going into bulk like a single crystal, which you have seen, very complicated. Whereas thin film deposition systems are inexpensive, is there, and material is also less required. So it becomes economical. And there are the two main deposition, physical deposition technique and chemical vapor deposition technique, two main techniques which we are using. And we started with the physical vapor deposition technique, and in this we were discussing about the thermal evaporation. But before going into that, we have discussed like what are the different way the thin film grows. So we saw that there is an island growth method, and or there is a layer by layer growth, or there is a combination of island and layer by layer. But before going into that, there is like what exactly is happening during the thin film evaporation process. So we know that like when we were talking about thermal evaporation or electron beam evaporation in our day before yesterday lecture, we saw that we are evaporating the material, right? And then they are going and sitting on the, our substrate is there. So what is happening on the substrate? So if we can understand that, then we can understand ki what are the parameters which we can be changing to get a good film or a very structured film or a film for a given application. Because some application required that the film should be a single crystalline, very smooth. But in some application you require voids or you require a structured film, like very small grains are there, more surface area, so that you can absorb material, or catalysis is there, so something like that. So what are the processes which happens on the substrate during any thin film growth? So like we have got this, these are the atoms which is coming and getting deposited. This is our substrate, this is our substrate, and this is the incoming hot atoms are coming. It's like say in case of a thermal evaporation. Now on the substrate, this comes and sits here. So this is the deposited atom, this is deposited, this is deposited. But it does not happen that they come and sit at one place. So they, because we have learned that it can be like island growth can be there or a layer by layer. So they will be moving within the substrate, and there will be some like cluster formation is there. So it can be a 2D cluster or a 3D cluster, and wherever there is an island formation, so 3D cluster is like an island formation, island formation, or this can lead to layer also, depending on the interfacial energy, the surface energy. Okay. Now, but this is one cluster which is forming here. What happens when another atom is like coming? So this atom has just now come and set here. So it will try to get added to this. So it is like diffusion to the cluster and nucleation, or it can form a new nucleation center here. So it can be diffusion to cluster is one thing. It can so also happen that it gets re-evaporated from the surface. Sometimes because if we are like maintaining the substrate at high temperature, so there is a tendency of re-evaporation. So this is basically a dynamical situation where there is cluster formation, there is a 3D nucleation, there is migration of coming add atoms, and there can be re-evaporation also. So depending our kind of application, we have to optimize our growth process. So growth of thin film is a highly non-equilibrium phenomena, and pressure in the gas phase is much less than vapor pressure, and particles have high energy compared to the substrate temperature. So whatever is coming and sitting here, they have got very high energy. Now, process during growth is diffusion of atoms on the surface, like this is going and sitting here and those things. Nucleation of 2D island or a 3D cluster. Phase formation for compound films, if you are like evaporating two different materials together for the compound formation, so there will be a phase formation. And generally when there is a phase formation is taking place on the substrate, you have to give some energy also, and in those cases the substrate is held up at high temperature. Then there can be re-evaporation or ripening and coalescence. So re-evaporation is there, so you have to, the substrate temperature has to be maintained so that the re-evaporation rate is much less than the rate of the growth of the film. And then obviously the clusters will be coalescing, and they can be either forming the layers, or they can be forming the island, depending on the type of the growth we are looking into. Now, what are the parameters which affect the film quality? So one is the substrate and other is the deposition pressure. So substrate lattice parameter is very important. So this, like, your substrate can be itself a crystalline like a silicon, or it can be glass also, which itself has got no structure. So depending on your substrate's crystallinity also determines the structure of your film. So if you are using a polycrystalline substrate or a glass substrate, so it is very difficult to grow a crystalline film on it. Why it is so? That because we will be coming to that, it is the epitaxial or the polycrystalline nature. Second is reactivity with the substrate. So if your substrate is very reactive, you are depositing it on a, say, a metal like aluminum foil or something, and there is a reactivity, so there can be impurities can also come, or there can be doping, unnecessary unwanted doping, all those things can happen. And the surface free energy will lead to, it can be either layer by layer growth or the island growth. So this we have already talked in the last class. Second is the deposition pressure. Like what is the pressure inside the chamber, in your deposition chamber at the time of deposition. So why it is important is, one is like it affects the purity of your film. So if the vacuum is not very good inside, no, you are depositing at a high pressure, so there can be like your those atoms, the gas atoms, like in case of sputtering, which we will be studying today, we have got argon. So they can get incorporated. Or sometimes you want that there can be some kind of reaction, like when we will be coming into the chemical vapor deposition, we will see that there we want reaction. So it affects the purity of the film. Means it can be good or it can be bad. And it may also include the surface free energy. But main effect of the deposition pressure is the mean free path. What is the mean free path? So mean free path is like, it is the distance traveled by any atom in the given environment before it collides with the another, or the time it takes when before it collides with the another atom. So when it is 1 atmosphere pressure, so the mean free path is in microns, and not even microns, this is in 10⁻⁶ centimeter. Okay, so very less, no? So if we see it in meters, so it will be 10⁻⁸, so like 10 nanometer. So the mean free path of a given atom is like 10 nanometer in when there is a pressure of 1 atmosphere. So if we have a chamber, what is the time for monolayer? So this is monolayer formation time. It means that if I have a substrate, here we have a substrate and it is clean. Say it is just silicon. We have got just silicon atoms on it. Only silicon, pure silicon. Now it is inside a chamber. We have a chamber here which is at 1 atmosphere with, and air is there. So in air, what we have got? We have got oxygen and we have got argon, nitrogen, and all those things. So there will be a formation of some oxygen, and these atoms will start sitting here. And within 2 nanoseconds, within 2 nanosecond, one layer, single atomic layer will get formed on this silicon. So the surface of your silicon substrate will not remain as silicon. There will be one monolayer formation within 2 nanosecond, which if we don't want, then we should have a better pressure. Now if we go to 10⁻⁶ torr, which we generally get by using a combination of a rotary and a diffusion pump. So the mean free path increases to 50 meter. 50 meter is the distance one atom will travel inside this kind of vacuum before it encounters another atom and gets collided. So, and the time for monolayer formation because of the environmental gases is 2 seconds. And if it is 10⁻⁹ torr, which is a ultra high vacuum, which you can get using a sputter ion pump and all those things. So the mean free path increases to 50 kilometer, and the time for monolayer formation is 31 minutes. So if you want to get a very good single crystalline or even polycrystalline, but a good quality thin film and high purity thin film, you should be having a pressure of this kind inside your chamber. If anyone of you is having any want to discuss something, please let me know. So So we will be using this kind of vacuum because first thing is the mean free path is increasing. How the mean free path is important. Now I have, this is my substrate. We again go back to and thermal evaporation. So if you remember that day. So I have a coil, I am passing some current through this, and the material which I want to evaporate, I am putting it in a some crucible or some. So say I am evaporating gold or silver, and I'm passing the current, so it will get evaporated and atoms will come and sit here. And we will form a AG film on this, right? Now, in a general system, this distance may be say 10 centimeter or say 20 centimeter, right? Now, if I am having a pressure of 1 atmosphere inside my, so I have a pressure of 1 atm atmosphere. So this AG atom, which has just come from my filament, it will be just traveling this much distance before it encounters a say oxygen molecule or a argon molecule. So only this much, and it will, so before coming it will not be able to, basically there is no chance of this AG evaporated AG atom to come and sit on my substrate. So when I am depositing it, so you can just think like 1 atmosphere is like I'm just putting some silver in a beaker or alumina crucible and hitting it. So do you think that if I put a like a substrate on top of it at a 10 centimeter, or you will get a thin film or a proper thin film from it? No, there will be a lot of evaporation will be obviously there, but it will be like contained here only, whatever is the vessel in which it is kept, the crucible in which it will get deposited there, but we cannot have a uniform thin film. But now we come to a 10 power minus 6 vacuum here. Okay. So we have, instead of now 1 atmosphere, we have a 10 to minus 6 torr. So this AG, now again this AG is come, it will be traveling 50 meter before it encounters anything else in its path. So this will evaporate here and directly come and sit here. This atom, if it evaporates it will come and sit here. And then whatever surface kinetics is there, it will form different clusters and whatever. That is a surface phenomena of the substrate. But in between the evaporant and the substrate, it will be, this path is free. No disturbance is there in this path, no disturbance. So that is why when we are depositing a good film, we want to have maximum mean free path for our evaporants. So that's why vacuum is important. Okay. Now coming to the physical vapor deposition, we have already started that. So just thermal evaporation is there, electron beam evaporation. These both things I have taken explained you in the last class. So just a very brief review. So we have, in the thermal evaporation, we have a chamber, and this is generally minus 6 torr or minus 5 torr. This kind of, we are having the vacuum using vacuum pump. We are getting this, and then we are keeping the material in a substrate, in a crucible. So this can be anything like a resistive wire can be there, or it can be a alumina crucible or a tungsten crucible, all those things. So my material, like if this is AG, so it is there, and we have the substrate which is holded at the top, or it can be upside down also. We can have upside down evaporation also. And this is my evaporant and this is my substrate. Both is possible in this configuration. Because it can be like we can put a wire and on that we can keep our evaporating material, and like metals are there, we can put a wire inside this. Like if we have this wire helix and we can put our wire inside this of AG, EU or aluminium, anything. So we can do a top down or a bottom up. And this thermal evaporation we can use. So generally crucible is heated using a tungsten filament. And if we are using a electron beam to heat, why we have gone from the thermal evaporation to the electron evaporation? Because many materials we cannot just pass the current and heat it. It can be having very high melting point. To reach that kind of temperature, we are using a beam of electrons, because beam of electrons can have very high energy. So generally if we are using oxides are there or nitrides or some material, a compound is there having very high melting point, so we are using a electron beam evaporation. But in this case, the system becomes more complicated. We have a magnetic field which is like bending our electron beam, and then should have a cooling water circulation inside the around the crucible to it keep it at a low temperature so that the crucible itself does not melt. So these are the complications. So you see that how this thin film deposition techniques are evolving. The most suitable, the most simple is the thermal evaporation system. Here, it is very like rudimentary. It can be have in any lab, you can have it. You are just evaporating the material and depositing it. But every material you cannot do like that. And then you are coming to the electron beam evaporation, which is like a thermal evaporation but with more sophistication. Now, in all these things, like in the first slide also I said that depending on the substrate also, the kind of films we can deposit. So it is when we are using a single crystal substrate. When we are using the single crystal substrate and we wish that the film which is growing should take up the crystallinity or the crystallographic relationship of the substrate, so it is called the epitaxial thin film growth. So what is basically epitaxy? Epitaxy means growth of a film with a crystallographic relationship between the film and a substrate. So if we see this diagram, we have a substrate. It can be say silicon or it can be strontium titanate or sapphire. Now this is the ABC parameter. So say silicon. So this is say unit cell. So this distance is say A of silicon. Your crystallographic A. Now when I am growing another material on this, so it can be homoepitaxy or it can be heteroepitaxy. Like if you remember, we studied homogeneous nucleation and heterogeneous nucleation. Remember? All of you remember or no? Answer me first. Homogeneous nucleation and heterogeneous nucleation in single crystal growth. Looks like there is no one listening to the lecture. Someone is there, okay. So remember that.
Yes, ma'am.
Yes. So here also we have got homoepitaxy and heteroepitaxy. Very similar. Now because this is also nucleation. In that case also we were trying to nucleate the single crystal on a seed. Here our seed is the substrate, right? And our single crystal is the thin film. So what happens in homoepitaxy? Silicon on silicon. Say my substrate is also silicon and my crystal or the thin film which is we are going is also silicon. So silicon on silicon. So in this case what happens? Your A of the lattice parameter of substrate and of thin film is same. So wherever the atoms, add atoms which are coming after the evaporation, they will be coming and sitting exactly at the crystallographic position. So it is called the homoepitaxy. And in case of heteroepitaxy, so we have got a different substrate, hetero. So my seed is different and the material which I am trying to grow is different. So like aluminium arsenide on gallium arsenide, or say gallium arsenide on silicon. So we have there will be a mismatch, lattice mismatch, right? So so then how the lattice mismatch can be there? It can be two types. Either my lattice is smaller lattice of growing film. Say it is AF and of my substrate is AS. Facing difficulty connecting via the wave continuously, it is loading. I will let it know, I will inform our IT team to see if there is any problem from our side. Are everyone facing this problem with WebEx? Other people who are joining? Or is it just one person?
No, ma'am, there is no any problem.
There is no problem, no? So, whoever is having problem, please look into from your side because others are not facing it, right? Okay, then maybe you can log in on to the YouTube also and see from there. Okay, anyway, we were talking about the lattice mismatch of the substrate and the growing film. So let our film lattice is AF and substrate is AS. So AF can be larger or it can be smaller. For when it is equal, it is homoepitaxy. Homoepitaxy is AF is equal to AS and same material. But so if the lattice is bigger for the film, so this is the case, okay, for the greater one. So what happens? There will be initially there will be strained. It will be relaxed. So if it's like here, you can see that it is like two initially, like there will be some mismatches there. So few initial layers will be relaxed and then it will take up its own value. So this is called the heteroepitaxy. And or if it is less, so initially there will be fewer numbers and later on it will follow its own growth. So initial few layers will be strained or initial few layers will be relaxed and then it will take up its own crystalline lattice. So when you are growing a thicker film, say more, these are like one monolayer, this is one monolayer. But when you go to say 10 monolayers or 50 monolayers, so your grown film will be a single crystal. And it will have its own lattice. So this it will not follow, it will follow this. The lattice of the film will be followed. But initially at the lower layers, there can be strain or relaxation. But as it starts growing up, it will slowly get into its own form. So here in this photograph, you can see this is its actual. This one is its actual, but it will be growing and then slowly it will take this its own natural lattice and then it will be a proper film. Okay, so there we have got homoepitaxy and heteroepitaxy. So my first question for today is like homoepitaxy and heteroepitaxy, and we have got homogeneous nucleation and heterogeneous nucleation. So how these two phenomena are similar? And just write one according to your understanding how homoepitaxy is similar to homogeneous nucleation and how heterogeneous nucleation and heteroepitaxy in case of thin films and in case of single crystal growth. These two phenomena are basically same, though we are using two different terms. So just give me your understanding. Whatever you have understood till now, just give me the answer in one or two lines. Okay? It's clear to everyone?
Ma'am, please repeat the question.
My question is like we have got homoepitaxy and heteroepitaxy now. We have learned now. And earlier we have learned homogeneous nucleation, right? And heterogeneous nucleation, right? So these, so basically I want your answer like heteroepitaxy and heterogeneous nucleation are same. Similarly, homoepitaxy and homogeneous nucleation, this phenomena is same. So why it is so? Give me your explanation, how you understood this thing. That these two phenomena are actually same thing. And these two phenomena are same thing. So how it is so? Right? So these are few more examples like homoepitaxy. We are using gallium arsenide substrate for the growth of, and the film is also gallium arsenide or silicon on silicon. But heterogeneous is like gallium arsenide we are growing on the silicon substrate or gallium nitride on sapphire substrate. So epitaxial films are purer than the substrate, low growth temperature. Layers can be doped independent of the substrate uniformly. So it can be doped, but the basic material is the matrix remains the same. In case of heteroepitaxy, we can do band gap engineering is possible because as I said, why band gap engineering? Very initial layers, they are strained or relaxed. So in that way, your surface effect starts happening. So you can have some band gap engineering at very low thickness. Similarly, we can make quantum wells, quantum dots, all those things. Now coming to the epitaxial thin film growth technique. So one of the most important epitaxial thin film growth technique is the molecular beam epitaxy, MBE, more known as the MBE. This is basically a thermal evaporation. It is not doing anything other than thermal evaporation, but it is a very sophisticated instrument. Why it is so, I will just explain. So first, let us go into this word. What does it mean? Molecular beam epitaxy. So where the beam is coming. So this beam word is used because here the vacuum level inside the chamber is in 10 to the power minus 9 or even 10 to the power minus 12 torr. 10 to the power minus 9 to 10 to the power minus 11 torr. If it is so less, vacuum means pressure is so less, vacuum is so high. So the mean free path, we were talking just mean free path of your atoms, of whatever is evaporating, it will be in kilometers. So it will not, so if I have it is evaporating from this. So if some material is there and I am evaporating it, so it will form a beam like this. The material will be forming a beam. So you can see it here. So we have got this beam kind of thing. So here the evaporation is not happening from a wire or we are using a crucible. So it is called Knudsen cell. We will be coming to that. We put the material here and there are shutter, and when it is evaporating, it forms a beam of the molecule. Say like this example is there for like gallium arsenide and all. So it forms a beam. So this is the full system is there, and this is the actual system. So in this actual system, this full chamber is the MB chamber. You have got the material which you want to evaporate is from here. So these cells, there are cells in which the material is put. So these are called the effusion cells, effusion oven. So here we put the material. They are kind of crucible, but very narrow crucible with a very small opening. Why small opening? So that it forms that beam. Beam formation is important here. And in front of the, so individually all these cells can be heated to at a different temperature. So if you want to do like layer by layer deposition, or like in this example I'm showing like gallium, this is gallium is there, this is gallium, sorry, just wait. Sorry, huh? Some disturbance was there. So so here, so this is just wait. So this is basically gallium is there. This is arsenic. Okay. So we can individually this cell we can individually heat it so that we get a molecular beam of gallium and arsenic. We can have it together or at different time also. And if we are using any dopant or anything else like there is aluminium is there, tin is there, so we can their stoichiometry, the amount, their concentration we can change, so we get lot of handle on each parameter. So this is the material is kept here. They are heated. The cells are heated, and then our substrate, substrate holder is here. So it is kept here on which we want to grow, and it is rotated. So there is some rotation is there. Why rotation we are using? Because so that the film which is getting deposited on the substrate is uniform, and vacuum is there. And then we have other, we can be also, there can be we can put some characterization facilities inside this chamber to see how the film is growing, so it can have lot of sophistication. So process of thin film deposition by MB is nothing by high purity single crystal film is grown one atom or molecular layer at a time under ultra high vacuum condition. Physical evaporation of the source material is carried out in ultra high vacuum environment like 10 to minus 8 to 10 to minus 12 torr also. Evaporated atoms or molecules travel in a straight line, collision free path. So because of this collision free path, this. So this kind of vacuum ensuring that the path is collision free. If we are going to a less vacuum, there will be collision to a heated crystalline substrate where they adsorb and form an ordered single crystal layer. The source material can be like example elemental gallium and arsenic for gallium arsenide film are placed in separate high purity crucible with effusion cells also known as Knudsen cell. These cells are heated to specific temperature, causing the material to evaporate or sublime and form a direct beam of atom or molecule, depending whatever you are picking. The temperature of each cell is precisely controlled to adjust the flux or the rate of arrival of each constituent material. The low deposition rate, so the temperature is so that the deposition rate is very less. So typically a few atomic layer per second. So why we are keeping the deposition rate so less? Because we want to have a very uh, good crystalline film. There should be less dislocation, less voids. So, and high atom mobility promotes a layer by layer growth. So basically this MBA technique is used where we want a very high quality material. So generally it is used for in semiconductor industry like gallium arsenide and all those things. The growth process can be monitored in situ, like we can put, so earlier if you remember, in case of a thermal evaporation or in case of a electron beam evaporation, we were monitoring the growth rate of growth using a crystal, no, this quartz crystal thickness monitor. But here analytical tools like, no, read reflection, high energy electron diffraction, this can be used because they give you information. This read is there, lead is there, low energy electron diffraction. This gives us an information about how this layer is forming. So whether, so if you want to study the layer by layer growth or it's an island growth, and which if you want to find out the rate of growth, so this kind of uh, techniques you can use in with along with the MB instrument. Mechanical shutters are placed in front of each cell and can be opened or closed in a fraction of second. So if you like want to use something as a dopant and very low concentration of dopant, so you just put it, the shutter is there. When you want to dope it, you open the shutter, it gets evaporated, then you again place the shutter back. So the evaporation stops. This allows for rapid and precise change in the composition and the doping of the growing layer, enabling the fabrication of complex layered structure like quantum well and superlattices. So now coming to one more deposition technique, it is the sputtering. So till now we were like giving, heating the material. All the three techniques which we have read till now, we have studied till now, we are heating it by different techniques. We are passing the current, or we are putting a fusion cell, or we were using the electron beam, but we were basically hitting the material. Now we will be using sputtering. So what exactly is sputtering? Sputtering is a process where atoms are ejected from a solid target material due to bombardment of the energetic particle. It is basically the momentum exchange between the ion and the atom in the material due to collision. So generally, so this is like, this is my target of which I want to deposit the thin film of. And we have an atom or ion with high energy. So it comes and bombards the surface. So what it happens, it bombards the surface, and because of that, some ions or atoms of the surface will be dislodged, and then they will go and set on the, my substrate is there. So they will start, this is my substrate, and it will start forming the film. So it is basically an energy transfer process or momentum transfer. So, and for this we generally use argon because it is inert, so there will not be, and it is heavy. So you want a heavy atom which has, or ion with kinetic energy, and it should also be inert. It should not make a compound in itself. Now there are like different configurations of sputtering. So it can be a direct current sputtering, DC sputtering they call, or a radio frequency or magnetron. So what happens in a DC sputtering? Nothing. We have the target and there is a power supply and we have the plasma. Why plasma is required? Because you have to ionize the gas, then only it will come and set. So we have the argon, AR positive ions are there. So we have to make the AR positive. So we are making a plasma by using this, and this your target is at a negative potential. Okay, so this will be coming and hitting your target, whatever material you want to deposit, and it will be dislodging the atoms from it, and they will come and set on the substrate. So normally, this is very normal, basic. So this is a DC sputtering system. So now this plasma depends on the argon pressure inside the sub. This is a chamber is there. So what is the argon pressure? So initially, if your now here you can see in just earlier we were saying that we should have a good vacuum, then only we get a good film. So there is competition. You want a plasma also and you want good vacuum also. So generally we see here that around 100 millitorr kind of pressure is the best for striking the plasma also and depositing the film also. If it is very less, then the deposition rate, the number of argon ions will be very less. And if we go very high, so there will be lot of collisions of the whatever it has come out, whatever ions are coming out from your target, they will start colliding with your argon ions. So therefore, the deposition of film will also deposition rate will go down. So this is like around 100 millitorr of temperature of pressure. We will get the best film. Now, what is happening? We are having the electrode, the material on which, so it is negatively biased. We have a argon plasma and wafer is here. And you do vacuum. So here we can see in this what are happening. This voltage is there. We have the target. Argon ion is coming and bombarding here. And one atom is getting dislodged, which comes and set here. So from here, atoms will be coming and setting. And argon atom can also interact with this whatever target atoms is coming down, and there can be resputtering also. So it can also happen that the argon atom is colliding with the coming atoms, and because of that the deposition rates are very less. So plasma is needed to make the gas conductive and generate ions, then it can be accelerated to strike the target. High pressure than evaporation. So in evaporation we were going into like 10 to power minus 5 and all, and here it is like 10 millitorr. Better at depositing alloys and compounds than evaporation. So here what happens now, it is not like one atom it is coming out. The energy transfer can be to a given molecule also. So if I say I have a SiO2 molecule is there. So energy transfer can be this argon ion when it bombards the substrate, full SiO2 can dislodge and come and set on. So it is easier to form thin films of the compound material here, like any oxide you want to deposit and those things. Or if there is an alloy, so then also it is good. The plasma contains equal number of positive argon ions and electrons as well as neutral argon ions. So equal number of positive argon ions and electrons are there. So what is happening? Our positive argon ion is hitting our target, and electrons. So all electrons, this is because we are putting a DC voltage. So what happens after some times, there is a charge layer forming, which decreases the deposition rate further. So this is this stops the deposition of thin films in case of a DC sputtering. So before we go into remedy for this, so what are the advantage? It is able to deposit a variety of metals, insulators, alloys and composite. It will replicate the composition of the film target in the film. Capable of in situ cleaning prior to film deposition, means we can use the plasma so that whatever if there is any impurity on the substrate, that plasma can clear the impurity. Better film capable quality and step coverage than evaporation, because wherever the plasma will be there, there will be an deposition. So in case of evaporation, it is coming in a cone and there will be some deposition will be different at different. If you are using a very big substrate, so the thickness of the film will be different at different places. Whereas in case of a sputtering, wherever the plasma is there, you will get a similar kind of film. This is partly because add atoms are more energetic and film is densified by in situ ion bombardment. It is easier to heat up to high temperature than evaporation in vacuum. It is more reproducible, same deposition rate for same process parameter. So easy film thickness control via time. Can use large area target for uniform thickness over large substrates. Sufficient target material for many depositions. So if you have one target material, it can be, you can keep on using it. Whereas in case of thermal evaporation, so whatever you do, whatever material you take, you evaporate it and finish it in one time. So every time you have to put your material, and there is no X-ray happening like in case of electron beam. Disadvantages, there can be substrate damage due to ion bombardment or by the plasma. So electrons which is there in the plasma, it will be coming and bombarding. So the substrate can get damaged, or it can also damage your film, growing film. You are using high pressure, so more contamination. So there can be some argon incorporation in your film. Deposition rate for some materials are quite low, and some materials like organic, they can degrade due to ion bombardment, so we cannot use them. And most of the energy incident on the target becomes heat, so we have to generally cool the target. Now, what are the dependence of deposition rate? So high chamber pressure means less mean free path. So therefore, a typical target substrate separation is mainly centimeter. So sputtered ion have to go through tens of collision before reaching the substrate. Mean free path is there. So here our vacuum is 100 millitorr. So there will be many collisions before it reaches the substrate. So this reduces the deposition rate, one thing. Considerable material are deposited onto the chamber wall, and too many collision also prevents ionization. So there is a very slow deposition, and sometimes there can be like dissociation also. For low chamber pressure, for same power, high ion energy, then that increases. So you have to have more power, you have to give for more power, like you have to give like DC sputtering is there, so more voltage you have to put. So but fewer argon atoms to bombard the target for deposition, which reduces deposition rate. So lower chamber pressure means you have to your number of argon atoms are decreasing, so there will be less deposition rate, and maybe you can increase it by using higher voltage, which is also not very good or easily making. Therefore there exists an optimum pressure, we have seen that, for maximum deposition rate. This optimum pressure depends on target substrate configuration. Now we come to the RF sputtering. Just I will take 1 minute break and then I will be back. Okay. Now from the DC sputtering, we go to the RF sputtering. So as I said that in DC sputtering, we have got the argon ions and we have got the electrons. So what happens? The electron starts building up. Even argon will start building up. So this charge buildup is then it decreases the deposition rate. So RF sputtering tries to look into that point, that how to change the charge buildup. So frequencies less than about we can use frequencies less than about 50 kilohertz. So electrons and ions in the plasma both are mobile. Both follow the switching of the anode and cathode. So we have got in this now we have earlier the substrate was at the target was negative charge. Earlier in DC it was negative and this was positive. Okay, but now we have gone to a RF, and so that their polarity will keep on changing like I have shown here. So polarity is changing here. So the electron, we have electron argon here and electron minus. So they will both follow the switching, this RF switching. So basically DC is sputtering from both surface. So there will be like what happens, this will sometimes hit here, this will sometimes hit here. So then it is of no use. So if we go to very high frequencies, now we take a case when we go to frequency above 50 kilohertz. So the heavy ion can no longer follow the switching. So argon will no longer able to follow the switching from the positive polarity to the negative polarity, whereas electrons can move. So electron can be moving to this side and this side, electrons, but argon will not be. And in this case, generally along with the RF. So RF bias is there and the target is negatively biased separately. So there is a negative bias target so that argon is always hitting the target. And there is a switching also. The RF is also there so that the electron will be moving on both the side, and if there is any space charge effect which is happening, there is a cumulative buildup of argon at on any surface on the target surface, so electron will be neutralizing that. So ion heavy atoms ions can no longer follow the switching and electron can neutralize the positive charge built up. This is good for insulating material. So another way of taking care is like if we just ground it, so electrons can go away, but if it is not there, it is, so it is good for insulating material. So target, if it is a insulating like SiO2 or Al2O3, so this is a insulating material. So wherever whatever argon is coming here, it stays here. So after the bombardment, it is staying here. It is not moving out. So then this becomes positively charged in case of DC. Though it is negative, but here we have got a layer, the space charge layer. So it will stop. So now this electron which is coming. So this electron which will be coming now, it will be neutralizing the argons which have. So good for insulating material because positive charge built up on the cathode in DC sputtering system can be avoided. When frequencies are less than 50 kilohertz, both electron and ion can follow the switching of the anode and cathode, basically DC sputtering of both surface, which we don't want. When frequency is well above 50 kilohertz, ion can no longer follow the switching and electron can neutralize the positive charge buildup on each cathode. So this is just to avoid the charge buildup. We have gone from the DC to the RF. Now there is something called the magnetron sputtering. So magnet, so we are using a magnet here. So why we are using the magnet? But it can be used with both DC or RF. So in both we can put the magnet. So the goal here is to have a high sputter rate at low argon pressure. So now we from 100 millitorr we can go as low as 2.5 millitorr. Why we want to have a better vacuum? Because the quality of the grown film is better in case the vacuum is better at a low pressure. There will not be much dislocations, and the sputtering rate also becomes high. So how the introduction of magnetic field is increasing the sputter rate is like increase the probability of electron striking the argon. So as we know that when there is a magnetic field, so we have an electric field between this, and we are putting a magnetic field inside, cross inside. So anything which is getting argon is getting ejected, it will start forming a curvature path. So it increases the electron path lengths, and we are so increase the probability of electrons striking the argon. So whatever electrons are there or argon is there, the striking will be more. So more and more ion formation will be there, and so and it can be used we are using both the electric field and the magnetic field, and it can be used with both DC or RF. So so in DC and RF sputtering, the efficiency of ionization from energetic collision between the electron and gas atom is low. So most electron lose energy in non-ionizing collision or are collected by the electrodes. To increase the deposition rates, magnets are used to increase the percentage of electrons that take part in ionization event, increasing the ionization efficiency. A magnetic field is applied at right angle, right? Because we have to introduce a spiral kind of pathway for the electrons. Right angle to the electric field by placing large magnets behind the target. This traps electron near the target surface and cause them to move in a spiral motion until they collide with an argon atom. The ionization and sputtering efficiencies are increased significantly. Deposition rates increase by a factor of 10 to 100 to around 1 micrometer per minute. That is the deposition, thickness deposition. At lower argon pressure also you can sustain a plasma and can be utilized since ionization efficiency is larger, which improves the film quality as less argon will be incorporated into the film. Magnetron sputtering can be done in both DC and RF, but more often it is done in DC as cooling of insulating target is difficult. So we have this is the magnetic field. So it is like magnet assembly is there. So this is north, this is south, this is north. It is placed like that. And this is our target. This is the target. And behind it, we have got the magnets. So it will be, this is the magnetic field lines. And because of this, the electrons will be having a spiral path in this area. So the argon ions are accelerated to the target. So more argon ions are there. So electric field is there. This is the electric field direction. This is the magnetic field direction. So they are perpendicular to each other. So the sputtering rate increases. So this is basically magnetron sputtering. Now we can have reactive sputtering also. So what do you mean by reactive sputtering? So we are sputtering and presence of a reactive gas mixture with argon. So if we want to decide a oxide film, we can use an oxygen with argon. If you want to deposit a nitride film, so we can put some nitrogen gas. So there can be some reaction is there. So sputtering a compound target may not give what one wants. This does not mean reactive sputtering will give what one wants. It's just one more thing to try with. So basically you cannot just Si I'm using as a substrate and I want SiO2 and I am using argon plus O2 gas. So it is not always, it doesn't happen that when we are just using SI, target is SI and I get a SiO2 film. But I can get what SiO2 minus X. So there will be some incorporation of oxygen. So certainly reactive sputtering can be done using DC sputtering, whereas compound target can also be used for RF sputtering. Chemical reaction takes place on the substrate and target. So both places our reaction is happening with the gas molecule. It can poison target if chemical reaction is faster than the sputter rate. Poison means our composition of the target can change. So we need to adjust the reactive gas flow to get good composition. Example like SiO2 rather than SiOX without incorporating excess gas. But also remember that we are now putting a reactive gas with the argon. Argon is a heavy ion, so it is useful in the ionization for the sputtering, for the momentum transfer. But if we are putting any other gas, so there will be argon is also colliding with that gas, whether it is an oxygen or whatever. So this decreases the sputtering rate. The sputtering rate decreases, so the rate of the formation of thin film also decreases. So that's why generally reactive sputtering is a very slow process and not always used. So so just an example where we are using like for formation of oxides like alumina, silicon oxide, tantalum oxide. So oxygen is mixed with argon. Then nitrides we use either nitrogen or ammonia gas can also be mixed. For carbides, we can use methane and all hydrocarbons like for the formation of silicon carbide, tungsten carbide, etc. So if we are comparing evaporation and sputtering, so we see that rate of evaporation is very fast, thousands of atomic layer per second as compared to like one atomic layer per second. So it is a very slow process, sputtering. Then choice of material for evaporation is limited because it has to melt. Whereas for sputtering, it is generally almost unlimited, but okay, it is more, we have got more choice. Purity for in case of evaporation is better because there we are using it very high vacuum, and depending on the vacuum you are using, you get a very good film. Whereas in case of sputtering, because there are gas molecules, so there can be some incorporation of gases. Now substrate heating is in evaporation, there is no substrate heating because of the phenomena, whereas because in sputtering there is a lot of high energy molecules coming and striking, so the temperature of the substrate increases. So this increase in can also damage the surface. So which is very low in case of evaporation, but ion bombardment can damage the surface. In situ cleaning of the substrate is not an option in case of evaporation, but can be done in sputtering. X-ray damage can happen in evaporation when we are using an electron beam, and radiation damage can happen in case of sputtering because there is a plasma. Change in source material, we as I said in case of a thermal evaporation or any evaporation, the source material has to be changed every time, whereas generally in case of sputtering the target is placed once and you keep on doing it. Then decomposition of material is very high in case of evaporation, we are because you are going to the melting point of that material, whereas it's less chance of decomposition in case of sputtering. And scaling up is difficult because large area deposition is bit difficult, whereas sputtering it depends on your target, but the size of your target the film will be of the same size. Equipment difficulty is equipment is low cost, whereas it is more expensive because you are requiring a very high voltage. In case of RF you will need a RF power generator, then you may be needing a magnet is there, and then you are needing another gas, argon gas, high purity, so there is a lot of complexity and more expensive. Number of deposition, only one deposition per charge, where we can keep on doing deposition. Thickness control, in both of things you can do the thickness control, but with more experiments. And then we have got adhesion is very good in sputtering because energetic ions are coming, and there are other things. Now coming to one more kind of thin film deposition, which is the pulse laser, PLD, pulse laser deposition, pulse laser ablation. So here we are using a laser light to ablate the target. Ablation means we are hitting very small area of the target and it gets ablated. It in the same form means it is not dissociating. It is a very fast transfer of energy. So it is a highly non-equilibrium technique, and like target temperature at that point it can reach up to like 10 power 5 Kelvin, and very high electric and magnetic field because of the electromagnetic. No, we are using electromagnetic wave for the heating up, and then a plasma kind of thing is formed. So this you can see in this, no. So the laser light is falling. This is the target. So laser light is falling on this, and there is a like a blast of the material. Yeah, and ablated species are with the energy of like 1 to 100. There is a question like what are the application of sputtering? So all the application is in the thin film deposition, and sputtering is used for the deposition of like oxides and nitrides. So if you want to deposit an oxide film like SiO2, alumina, or similar kind of thing, or like nitride is it tungsten nitride, tungsten carbide, silicon carbide. So this kind of film when you want to deposit, you cannot do by thermal evaporation. You have to use a sputtering. Now coming to the laser ablation. So this is the structure. So excimer laser, generally KRF, krypton fluoride laser, excimer laser is used uh, with a UV wavelength. Why? Because you don't want it to heat the full material. Only a very small portion of the target should get heated at a given time. So this is focused on the target through a lens and mirror. It is focused, and the size of the laser beam on the target is very small, like it is in 1 millimeter dia. So very small area, the whole energy of the excimer laser is focused. And from there, the material gets ablated. So if say in this case, like I have shown, like very, no, you have got yttrium, barium, copper, oxygen. So it is material. This is a high temperature superconducting material. So this is a big compound. So when this laser pulse, and this is a pulse laser, generally pulses are there. So very high energy pulses are falling. So this whole molecules gets ejected from the surface of the target, and then this kind of plasma is formed. So this is called the plume, and this stoichiometry of the target molecule is preserved, and then it comes and falls on the substrate. So the substrate can be heated so that there is no dissociation, and thin film like crystalline thin films are deposited, and the target is generally rotated. Earlier we were seeing that the substrate is rotated, so substrate rotation can be kept like that, but target is rotated so that the wherever that laser is falling, it is not falling at the same point. There will be, it is falling at different points. So the step is like very high power excimer laser is focused on the target. The target is ablated to form a plume of atom molecules and chunks. So it will be, the advantage of PLD is that complex materials can be easily ablated, and the challenge is to maintain the stoichiometry. So whatever is the stoichiometry of your target, the same stoichiometry is there in the film. So this is this kind of PLD, pulse laser deposition, is generally used in kind of like magnetic material or ferroelectric material, or this superconducting material, where it is a very big compound has got many elements and the stoichiometry is very important. So when we want to deposit a film of that, so in case of thermal evaporation, this kind of material, either its melting temperature will be very high, or it will degrade, it will dissociate. In case of a sputtering also, because the molecule is very large, so the proper momentum transfer and the full molecule will get sputtered out, and the same composition can be maintained on the substrate is very difficult. So in those case, laser PLD is used. It is easy to use technique for all type of material. You can do it for other material also, but it is ideal for oxides, as high TC means high temperature superconductors, and compound magnetic materials. Exact transfer of compounds at high energy suitable for formation of the phase. This avoids electron or ion bombardment of sputtering. Thickness may be easily controlled by counting the number of laser pulses. Disadvantage is small deposition area, because as I said, the laser, our laser diameter of the laser pulse is very small. So whatever plume is forming, so if it is like ability, so there will be a plume formation, and I will be keeping my substrate here within the plume. So at a given time, like 10 centimeter, one sorry 10 millimeter by 10 millimeter kind of uniform films are formed, or slightly more than that, like 1 centimeter by 1 centimeter. So very small area uniformity is there, and deposition of particulates can be there, because some chunks can get evaporated. So deposition method for some metals I have given here, like aluminium we can do thermal evaporation, silver, gold both thermal and sputtering, copper both thermal sputtering, palladium, platinum, because their temperature, melting temperature is very high, so we can go for electron beam, titanium, nickel, chromium, tungsten, so we can go either for electron beam or for the sputtering. Now this was all the physical vapor deposition method. Now coming to the chemical vapor deposition. So as the name suggests, there will be some chemistry involved. Hmm. So here the mass transport of the reactant in the bulk. So we are transporting some reactants. So it can be in gas phase, like, and there can be a reaction. So the reaction can happen in the gas phase, chemical reaction, or it can happen on the substrate after coming. So the mass is transported to the surface of the substrate. There will be adsorption of the reactants, and there can be a reaction. Then after the reaction, there will be migration of the formed molecule on the substrate, and then incorporation of film constituents and island formation, and whatever was the byproduct, it will get dissolved, it will evaporate, and mass transport of byproduct in the bulk. So just like so CVD is diffusive convective transport of depositing species to a substrate with many intermolecular collision driven by a concentration gradient. So what is the concentration gradient? Like we have some material is coming from this side. So its concentration is high here, and concentration where it wants to get. So if I want to, like on this, no, I'm depositing, here the concentration is less. So like here we have silicon hydride is there. So this we are depositing, and we want to deposit it in the form of silicon. So we have used a hydride, and there will be a breakdown. We are, so gas phase reaction will be there. So first there will be gas will be transporting to the surface, and then there will be a gas phase reaction. So and after that there will be surface diffusion. Then whatever precursor hydrogen was there, so it will become volatile and it will leave the substrate. So I'll just show it now. So CVD is a chemical process of making film, in generally used in semiconductor industry, but can there it can be used otherwise also. The substrate is exposed to volatile precursors which react or decompose. Like silicon hydride is there, so it decomposes into silicon on the substrate surface to produce the desired film. Frequently, volatile byproducts are also produced, which are removed by gas flow through the reaction chamber. So we have like deposition chambers we were talking about. Now we have a reaction chamber. And silicon, carbon fiber, carbon nanotube, silicon oxide, a lot of things, no, silicon carbide, these are generally deposited. So here we have got like gases are generally used because you have to have the reaction between them, chemical reaction. So we have a gas or vapor source, and through mass flow controllers, because if you want to have a given stoichiometry, you have to change their amount. So we have a mass flow controller, so that how much, which gas at what amount it is to be flown inside. So gas is going inside, and we have a deposition chamber, and whatever substrate wafer is there, it is kept inside the deposition chamber. The reaction will happen. So like here I've shown. So this is my substrate, say substrate, hmm, and these are the gas molecules which is coming. Okay, this is one gas molecule, and this is the other gas molecule. Now they will be reacting together and just forming this. This is my film, and rest of all will go out. So this is the chemical vapor deposition. So generally there are two types of chemical vapor deposition reactions. If we can differentiate in basic of reaction, this is the thermal decomposition and reduction. So like we are using thermal decomposition is like we are heating the gas, and so that it is decomposing and forming. So like silicon deposition from silane. So we have got a AB gas. A is the solid and B becomes a gas. So it is decomposing. So we have gone silicon hydride. So silicon is left and deposited, and hydrogen leaves, and silane is there, and it can be used to deposit different materials are there. Then coming to reduction, we can have a hydrogen gas. We are introducing hydrogen gas. In this case, like we can see, tungsten fluoride is there. So it is in the gas form, and we are introducing hydrogen so that there is a reaction. So reducing the material, and we are forming the tungsten film, and the rest of the hydrogen hexafluoride or hydrogen fluoride gas is going out. So these are the reduction is there, and thermal decomposition. And the system can be like, it can be, we can have a atmospheric CVD, or we can have low pressure. So depending on the kind of reaction is there, it can be, we can either use a atmospheric pressure CVD or a low pressure CVD. So in atmospheric pressure, this we have, so there is no vacuum is not required. We have a heater because a reaction may require high temperature. Source material and the carrier gas is taken inside. These are the substrate, and the byproduct goes out. And in case of a low pressure, we have got the our rotary pump is there, and all the vacuum pumps will be there. And here also we have got the it is, our material is loaded, our gas is loaded using the mass flow controller, and our wafers are there, like in case of silicon industry, and the reaction is happening inside, and we can also purge different gases from through this, and the byproduct will be taken out using the our vacuum pumps. So I will not come into that now. Before I end, this is the 2D and the 3D printing is also there. So this thin film deposition which I was talking till now, these are very old techniques, most of you must be using, and but now coming up one method is this 3D printing. So, what is 3D printing? So, it is not thin film technology. It is 3D as the name suggests. So, it will be a bulk material. And but it happens. This 3D is printing is happening from the thin film deposition only. So we understand that. So first we go to what is a 2D printing. So 2D printing is like whatever paper, on the paper you are printing. So printer, so it deposits the ink on a substrate which is your paper, and it predefined text or picture is there. So which is there in your computer. You have already written the letter or the document which you are printing it using your ink and the paper. So how it prints, it's calculate that on the piece of the paper at what distance it needs to place the ink. If it is a colored printer, so which color it has to print at what place. So the printer decides, taking from the blueprint from the your computer, it takes and then decides that at what xy coordinate on the given paper I have to put which ink, right? And then there is a xy stepper motor, which is like we have an xy, this is an x and y stepper motor is there. So it will be like changing your cartridge position, so where the ink is getting deposited. So this stepper motor places the printing head to exact position, and the ink is evaporated from the printing head into the paper. So this is a 2D printing which every one of us is using. So hence 2D printing or simply printing is the process of putting an image on a paper. Now how it gets to that 3D printing. So basically 3D printing is layer by layer 2D printing. So you have got one layer of 2D printing, then another layer of 2D, then another. Like this, you are making a 3D image. But uh, but it is a solid object, what you are getting. No, it is not on the paper. So how this solid object is forming? So 3D printing is a form of additive manufacturing technique where there are three-dimensional object is created by laying down successive layer of material. So this successive layer of material is 2D printing. But here material is not ink. It is not ink. It is some it can be metal or it can be a polymer, whatever you want to make the material of your bulk of. So 3D objects are quickly made at a reasonable size machine connected to a computer containing the blueprint of the object. So like in case of a 2D printing, you know what you want to type and what you want to put into the paper. So in a 3D also you have to first make the drawing, all the 3D drawing of the material which you want to grow. So the 3D image of an object is created using a CAD, a computer aided design software program, and this information is sent to the printer, your 3D printer. So we have got the design. So in the computer I have made this design. Now I transfer this design to the 3D printer. So the printer forms the item by depositing the material in layers starting from the bottom layer onto a platform. In some cases, laser or light or laser are used to harden the material. So initially, like from this, it goes here and this is our final. So this one layer will be formed initially, then one more layer will be formed, then one more layer will be formed. So our printer, some material is there which it is depositing on this platform, taking information from our computer aided design layer by layer. So the same printing is happening, but now every layer it will take information like from the computer, print it, then it will again take information about the next layer and then print it. So that way you can make the 3D object. So that is the 3D printing. So what are the steps involved? So you can have modeling, additive manufacturing takes place, blueprint from CAD and slices them into digital cross section. So say I want to like deposit a hollow cylinder. Okay. In between it is hollow. So my printer will take the blueprint for each layer. And this it will slice into digital cross section for the machine, and the machine will take guidelines for each layer for printing, right? And then what happens, so this is the modeling part, and then the machine reads the design and lay down successive layer of liquid, powder or sheet of material to build a model from a series of cross section. These layers, which correspond to the virtual cross section from the CAD model, are joined together or automatically fused to create the final shape. Now these are the layers. So how these layers join each other? So there are techniques to join. Either the material, one layer and the other material, they fuse together, or they can be polymerized in situ or ex situ. or they can be like given some laser light or UV light for polymerization, or some temperature can be given to harden them. So there are different types of 3D printing materials. So they are either thermoplastic, means temperature are given for them to fuse, or there we can have resins or metals or ceramics. So basically the 3D printing technology takes sintering, like I said, we can put high temperature or melting. So some polymer is there or some plastic is there which can be melted, and then during the printing they will fuse together. Or stereolithography is there, we will be coming to it. So sintering is a technology where the material is heated but not to the point of melting. Metal powder is used to for direct metal laser sintering, while thermoplastic powders are used for selective laser sintering. Melting methods for 3D printing includes melting of substrate prior to placing on substrate, means the head of the printer. So the material gets melted at the head of the printer and the liquid flows down and then it sets. So it has to be, and as soon as it comes in contact with the air, it becomes solid. In stereolithography, photopolymerization, we are putting some photon like UV or laser is used to create parts. Here, appropriate light wavelength is selected to interact with the material to selectively cure and solidify. So 3D printing has been categorized to different by the additive manufacturing by the principle is like binder jetting or direct energy deposition or material extrusion, material jetting, powder bed fusion, sheet lamination, wet polymerization. So these are like different methods which are being used. So I'm not going into all those things, but this is an overview of 3D printing which are used for making many devices nowadays. And in actual use, it is used in automobiles and aerospace and medical robotics, in medical implants, no, this human implants. So they are made by, because if you want to make very precise parts, so this is a very good and not very big size. If you want to make a small size 3D object with very precise control of some with some internal some design is there, so this is a very good technique. And you can also select the material for which you want to use it. Okay, so this is the end of today's lecture. So one question you have already learned, have you know that one was my question was like we have got heteroepitaxy and homoepitaxy, and you have learned heterogeneous nucleation and homogeneous nucleation in two different contexts. So how they are similar, that you explain me one point. And second question is like uh, when you will be when it is what are the conditions under which uh, you will be using a sputtering for say I want to deposit SiO2. Okay, film. So I will be using sputtering, right? That we know. We will not use thermal evaporation here. No, we will not use it. We will be using sputtering. So first question is why? Hmm? Why sputtering? And in sputtering, we have learned DC, RF, magnetron, right? So which you will be using? Among DC you will be using, or RF you will be using, or magnetron with RF or DC, which you will be using to deposit SiO2 film. Okay, got the question? Anyone there? Okay, I will see who is there, because answers should come to me by
Ma'am, yes.
7. Hmm? And before I end this session, let me know if there is any problem or you want to discuss anything. No, nothing to discuss.
Ma'am, please repeat the question.
The question is that I want to deposit SiO2 thin film, right? And I will be using sputtering for that. So first question is why sputtering? Okay. And second question is which method? Which method is DC or RF or magnetron? And if magnetron, so it is DC magnetron or RF magnetron I will be using. Okay, got it?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
And any other question from your side? You want any question? No question from your side. Everything was clear. Okay, good. I'm happy that either you are finding it very like trivial or you know everything. So good. And then next will be on Friday, my class 19th. And then there will be one class on 2nd of January after your vacation. And maybe I will try to give you your assignment either on 19th or on 2nd at the end. And whatever assignments I am giving you now, they will be also used for your evaluation. So as you know, in this we have got generally evaluation. For my portion it will be like 100 marks, so 50% will be assignment and 50% of the marks will be on the your viva. And for the assignment I will be giving few more assignments either on Friday or on 2nd of January, and whatever I am giving now also I will be considering it. Okay, so okay, thank you and see you on Friday. Have a nice time. Bye.